So for the final project, my modeling, I predicted the predicted value of potential energy, the PE. I modeled that using the data provided. There are a small number of features for. So you could try each of those individually or combinations of each of them. You could even try transforming them as well. But for the purposes of this project, I tried a simple model with one variable. I chose temperature. I thought, given that we're talking about energy and heat transfer, that temperature would probably have the biggest influence of these. And then I added an additional model for comparison purposes that used all the variables other than the predicted PE. The high idea behind them trying all of them is it's better to start off with too many than too few. And then the one variable temperature model was chosen to highlight both interpretability as well as the limitations of a simple linear regression. So for the model building, I split the data into training, validation, and test sets. Since I'm using Excel for my modeling, I did this manually. There are 9,568 observations in the overall data set. I chose 1,000 observations for my validation data set, which is roughly 10%, and another 1,000 for my test data set, again, roughly 10%. I left 7,568 observations for my training data set. So what I found is kind of as follows. So for the one variable model using linear regression for all of these, because I'm using Excel, the R squared value was actually quite high. It was 0.89, which is almost 0.9, which is very, very high. So I think the idea that temperature would have a big influence on potential energy at a power plant conversion is kind of borne out from that. I did do some mapping of that, some graphing of that, just to look at how it plots, and it plots very closely, which you would sort of expect given the high R squared value. And then for the second linear model, I did another linear regression, and I used all the variables. So I used the temperature, the pressure, and the other two as well. And then the R squared came out even higher, but not massively higher. And I'll talk more about that in a minute. So for validation, to actually compare the models, I took the formula from the linear regression on the training data and did that, ran that against the validation data for both models. And then if you give me just a second, for comparison, you could look at the mean squared error, but since you've got the same number of observations, I just looked at the sum of the errors, and you can see that the error, sum of errors, is much smaller for Model 2, or relatively much smaller for Model 2, just a little over half for Model 1. So that seems to bear out that Model 2 with all four variables is a more accurate model, more accurate model. Then I went to the test data and ran that Model 2 again, the predicted value against the actual PE, and calculated the error, and then sum that up, and you take the sum of that and square it and divide it by the number of observations, and you get the mean squared error. So what I took from this, one of the things I took from this is that if there was a large amount of data for computational purposes, the trade-off of getting a slightly better model by using all the variables may not be worth it. You may need to use just go with the temperature, or maybe the temperature plus one other variable. Again, for the purposes of this exercise, I didn't feel like I needed to explore each and every variable combination, but you can do it. And then we're also using linear regression. Remains to be seen what other models might do, although this one seems to have a pretty strong fit. And then, one thing you always have to worry about with linear regression is if you have too many variables, that you're going to be overfitting. So you want to be careful with that as well. So that's my project. Thank you.